Hi everyone. So in the last video, we saw how to evaluate certain types of trigonometric integrals. So specifically, we focused on integrals that were of the form sine to a power times cosine to a power, or tangent to a power times secant to a power. And basically, there were different rules for whether these powers were even or odd. And basically, these rules rely upon the fact that you're basically taking advantage of the relationships between tangent and secant and sine and cosine, being that they have a relationship with their derivatives, but also with these Pythagorean identities. And so that's why the numbers need to be even or odd is basically just to make all of the identities and substitutions work out. So in this video, we're going to be focusing on now integrals that don't quite fit this kind of form. So yeah, let's get into it. So the first thing that I put here is I just wrote down a list of what would be called integral table integrals. And so what I mean by that is that these are ones that if you come across them on a test, like usually I wouldn't just ask you just to take the integral of sine of x, for example, but along the way that might come up. And if one of these ones on this list comes up, you don't need to really do any work to show what the antiderivative is. And these ones are all ones that I would be on a test providing for you on a list. So most of these I think are pretty straightforward. So we hopefully all know the antiderivative of sine of x is negative cosine of x. The antiderivative of cosine of x is sine of x. Tangent, so we actually talked about this one when we did substitution. So how do we come up with the antiderivative? Well, we wrote tangent of x as sine of x over cosine of x, and that allowed us to then do a substitution. And so the antiderivative came out to be ln of absolute value of secant of x. So this next one, we haven't yet talked about this. So the antiderivative of secant of x. So if you're curious where this rule comes from, well, I guess first thing you can check for yourself that this rule works, because if you take the derivative of all of this stuff, you should get secant of x. If you're curious where this antiderivative comes from, I'm not going to go over it in the video, but if you're curious, you can look in the book. So you can see this one. This is in the book. And it's in section 7.2. Basically, there's just kind of a special trick they do. They multiply the integrand by something over itself, something that doesn't change the value of the integrand. And yeah, it's just kind of a funny little trick. And then a couple other ones. So the antiderivative of secant is, secant squared is tangent. And then the antiderivative of secant times tangent is secant. So basically the reason I'm mentioning this is just, I think when we get into all these different methods of integration, it can get a little confusing, and sometimes you might even forget that there are certain antiderivatives that you don't really need to do any work to figure out. So there are other ones that I could have put here. I'm kind of skipping the ones that are relating cosecant and cotangent, basically because those trig functions just don't come up as much in this class. That's not to say they won't ever come up, but they're not going to come up so much, at least in this section of the book. Okay, so the first thing I want to do is basically do a couple of examples that are kind of along the lines of what we did in the last video, but just a little bit different. So first one I want to look at is the integral of tangent cubed of x dx. So first, let's go look at our kind of strategies we had for tangent and secant and kind of see why we can't use those here. So this does tell us that if we have an odd power of tangent, we should have a method, right? But the problem is that when m is odd, you're supposed to save a factor of secant times tangent. And the problem is that we don't have a secant in our integral, right? Our integral is just tangent cubed, so we cannot use that method. So this is an example, the reason I'm going over this example is basically just to kind of let you see some of the little tricks that you might need to do in these integrals. Every integral is different. I wouldn't expect you to kind of know right off the bat how to tackle every different type of integral, but I think the more different examples you see, the more that will kind of add to your kind kind of your library of approaches that you might remember. And so in this case, what we want to do is we want to actually split this up into a tangent squared times a tangent. Okay, so why would we do this? Well, what's one of the things we talked about in the last video? We saw that you can rewrite tangent squared in terms of secant squared. So specifically, we saw that tangent squared of x is equal to 1 minus secant squared of x. So let's go ahead and put that in our integral and we'll see where that takes us. So now we have 1 minus secant squared of x times tangent of x dx. So what do we do next? Well, you might think, okay, well, we have, tangent and we have secant squared. Maybe we can do a substitution, but we at least cannot do that yet because the problem is that it's not just secant squared times tangent. We also have this 1. So the first thing we want to do is distribute. So if we distribute, we end up with now tangent of x minus secant squared of x times tangent of x. Okay, so what should we do next? Well, let's actually split this into 2 integrals. So why am I thinking of doing that? Well, we know what the antiderivative of tangent is, so we might as well take care of that on its own, and then we can just focus on whatever's going on over on this second integral. So we have minus the integral of, I'll just rewrite it in this order because I like that slightly better, tangent of x times secant squared of x. Okay, so we know that the antiderivative of tangent, we just saw that on the previous page, that is ln of absolute value of secant of x. Actually, I'm not going to write that down just yet. We'll wait till we finish this other one too. So how can we approach this second integral? Well, remember that one of the things you should always be looking for is if the derivative of one of your items is also appearing in the integral. So like basically if you have something in your integral and then the derivative of that thing is also in the integral, that's a sign that maybe a substitution will work. And so in this case, the substitution we can do is just if we let u equal to tangent of x, then du is going to be equal to secant squared of x dx. And so basically this whole secant squared of x dx, that will turn into du. So I mentioned this in another video, but I'm probably going to stop for the most part, like solving this for dx. If you wanted to, you could say, okay, dx is equal to du over secant squared of x and put that in and cancel. But you don't really have to do that. In most cases, if you can just kind of recognize, oh, okay, secant squared of x dx, that's exactly what I have in my integral. I can just replace that with du. Okay, so we now have the integral of tangent of x dx minus, so we can replace the tangent of x with u, and then we can replace secant squared of x dx with du. And so the antiderivative of tangent of x was, we saw ln of absolute value of secant of x. And then what's the antiderivative here? Well, that would be u squared over 2 plus c. And then the last thing we have to do is just to put back in the what u was, right? So we have ln of absolute value of secant of x minus tangent squared of x over 2 plus c. Okay, so next up, we're going to look at one that is, oh my God, I did it wrong. Oh, how did I do it wrong? It's so annoying. Okay. So specifically, tangent squared of x is equal to secant squared of x minus 1. So we can put that into our integral. Okay, so now what? Well, you might notice that we have tangent and we have secant squared, and the derivative of tangent is secant squared. So that's kind of a good sign that we might be able to do a substitution. However, we can't do it just yet because the problem is that currently we're not just multiplying tangent with secant, we're multiplying it with secant squared of x minus 1. And so basically that minus 1 would kind of mess with the substitution if we tried to do it now. But what we can do is distribute, and then from there we'll see that we can do a substitution. So if we distribute the secant squared, we end up with secant squared of x times tangent of x minus tangent of x. And now we can split this into two integrals, right? So we can rewrite this as the integral, I'll just go on the next line, the integral of secant squared of x times tangent of x dx minus the integral of tangent of x. And so now we're in pretty good shape because we'll see that we can do a substitution on the first integral, and then we know already from the previous page the antiderivative of tangent of x. So for this first integral, if we let u equal to tangent of x, well then du is secant squared of x dx. And notice secant squared of x dx already appears in our integral. So we don't have to, if you wanted to, you could say du over secant squared of x is equal to dx and put that in for dx, and then the secant squared would cancel out. But I'm going to stop doing that every time because I think there's a lot of times where that's not really necessary, and it's a lot faster to just say, oh, okay, well, I can see that du is literally in my integral, so I can just replace that with du. So when we apply our substitution, now we're going to have the integral of u times du. So this du, again, came from the secant squared times dx. And then we have minus the integral of tangent of x dx. Okay, so what is our antiderivative for this first one? Well, it is u squared over 2. And then for the second part, we have the antiderivative of tangent we saw was ln of absolute value of secant of x. And then we have plus c. And then the last thing we need to do is replace the u with our substitution, which was tangent. So really we have tangent squared of x over 2 minus ln of absolute value of secant of x plus c. So again, basically just want you to see that there's a lot of different ways these can go. And again, I don't expect you to memorize how to do every single different integral. I expect you to have kind of a bank of ideas of how you could approach things and be willing to try them. And if they don't work, to try something else. And again, that's just a really important part of this class, is being comfortable with just trying things and seeing if they work. And if they don't work, then, trying something else. Okay, so the next thing we want to try, or I want to look at, is the integral of secant cubed of x. So I actually put this one on the worksheet from the previous video, but I wanted to go over it because it is a slightly trickier example. So the way I want to start this is basically the same as how we started the last one, but we'll see that from there it actually goes pretty differently. So I want to split this up into secant of x times secant squared of x. So let's do, basically, you might think that we would want to do what we did up here, right? And put in the Pythagorean identity for secant squared. So that would be 1 plus tangent squared. And that might work. Actually, that might be a different approach, but we're going to do something different here. We're actually going to do integration by parts. So again, I wouldn't expect you to know that this is an integration by parts problem. I know because I have done this problem previously, but just kind of remember that that's something you can try. When you have a product of two things, you can always try integration by parts as a possible method. So what are we going to do here? Let's let u equal the secant of x and dv equal the secant squared of x. So why am I choosing that? Well, we know the derivative of secant of x, and we know the antiderivative of secant squared of x, and so it will work out. So the derivative of secant of x is secant of x times tangent of x dx. And then the antiderivative of secant squared of x dx is tangent. So let's put this together with our integration by parts. So we have u times v, so that's going to be secant of x times tangent of x. And then we're going to subtract, the integral of v times du. So that's going to be tangent of x times secant of x times tangent of x dx. So where do we go from here? Well, let's rewrite this as secant of x times tangent of x minus the integral of tangent squared of x times secant of x dx. And so now what we can do is we can rewrite tangent squared as using the Pythagorean identity, right? So we know that tangent squared is equal to secant squared of x minus 1. And initially that might seem like it's not the right thing to do. And so why is that? Well, because that will leave us with an integral that only has secants. However, we'll see that once we distribute this secant squared of x minus 1, we're going to get back to our original integral. And so this is actually going to be one of those ones where you end up with two of the same integral and you add it to the same side and use that to find the value of the integral. Okay, so let's see how that looks. So we're going to have secant of x times tangent of x minus, so now we have secant squared of x minus 1 times secant of x dx. Okay, so let's distribute it like I said and see where that goes. So now we have secant cubed of x minus secant of x. So let's split this apart. So we have secant of x times tangent of x minus the integral of secant cubed of x. So that one is our original integral. So that's what we're going to need to be combining onto one side at the end. And then here we would have plus the integral of secant of x, right? Because we had a two minus signs. And so we saw on the previous page that the antiderivative of secant of x is ln of secant of x plus tangent of x. So I'm going to rewrite this with our original integral again, because right, we started off with the integral of secant cubed of x. And so now we found that the integral of secant cubed of x is equal to secant of x times tangent of x minus the integral of secant cubed of x dx plus, and then as we mentioned, the antiderivative of secant is ln of secant of x plus tangent of x. And then we should have a plus c in here somewhere. Okay, so now what do we do? Well, we have this secant and another secant here, and so we want to add them both to the same side. We want to add, so now we have 2 times the integral of secant cubed of x dx is equal to secant of x tangent of x plus ln of absolute value of secant of x plus tangent of x plus c. And now we're almost done. Now we just have to divide the whole thing by 2. And so we're going to end up with the integral of secant cubed of x is equal to secant of x times tangent of x plus ln of absolute value of secant of x plus tangent of x. And I'm going to leave the plus c outside of the fraction, like this. And that is our answer. So definitely a tricky one. And again, like I wouldn't expect you to just know off the top of your head how to do this. And this is probably harder than one I would actually give you on like a test or anything like that. But I just want you to see all the different kind of methods that are out there. And there are a lot of different approaches you could have taken on this that, most of them probably would not lead to the correct answer. But yeah, just I think the more kind of different examples you see, the better off you'll be. Okay, so for the remainder of the video, we're going to focus on examples that make use of a few different trig identities. So I want to just remind you of some more trig identities. So the ones we're going to be focusing on now are going to be basically variations of the double angle formulas for sine and cosine. So just to remind you what those are, and I'll give you, by the way, I'll give you the trig formulas on tests and quizzes. Memorization is really not my priority in this class. So the double angle formulas, the one for cosine says that cosine of 2 times x is equal to cosine squared of x minus sine squared of x. And so from this formula, we can actually get a couple of other ones. So I just want to show you the other ones that will basically derive from this. So if you were to take this, this formula and replace the, let's say the cosine squared with 1 minus sine squared. You could do it either way. It will give us 2 different formulas, but let's start with this. So if you replace cosine squared with 1 minus sine squared, you would get this, right? And so let's actually simplify that. So that's cosine of 2x is equal to 1 minus sine squared of x minus another sine squared of x. And so that means that cosine of 2x is equal to 1 minus 2 sine squared of x. I guess I didn't really have to write this second step. Let me just jump straight to that. So we have 1 minus 2 times sine squared of x. And so what that means is we can actually express sine squared in terms of cosine of 2x. So I want to take this equation and now solve it for sine squared. And so what would that look like? Well, first we would want to let's add sine squared to the other side. Let's basically kind of flip the order of things, right? So I'm going to add 2 times sine squared of x to both sides. And then that means we have 1 minus cosine of 2x. And so from here, if we divide both sides by 2, we get sine squared of x is equal to 1 minus cosine of 2x over 2. So this is going to be a really useful trig identity because basically if we have the integral of sine squared, we don't know how to do that, right? We don't know how to take the antiderivative of sine squared. But if you think about it, we do know how to find the antiderivative of this right-hand side because we could split this into 2 fractions, one of them being 1/2, and then negative cosine of 2x over 2. That's a pretty simple u substitution. And so if you do this same approach, I'm not going to go through it, but if you do the exact same idea, but instead of, so at this step, we replaced cosine squared with 1 minus sine squared. If you do the same thing and you replace sine squared with 1 minus cosine squared, you'll get a different formula, one that says that cosine squared of x is equal to 1 plus cosine of 2x over 2. So again, I will give you these formulas. I just like to show you where they come from so you don't just kind of think they're magic, right? I want you to understand that these, these are related to facts that you learned in your trigonometry class. So one other formula that's going to be useful is if we start with the double angle formula for sine. So sine of 2x, that would be equal to 2 times sine of x times cosine of x. And so sometimes this is rewritten as the following. So you can rewrite, if you have sine of x times cosine of x, you can rewrite that as sine of 2x over 2. So we'll see how that can get used in integration as well. Okay, so let's do an example of a few different integrals that make use of these identities. So the first one I want to look at is a pretty simple one. Let's just do the integral of cosine squared of x dx. So basically, like we saw, we want to make use of that formula. So that formula says that cosine squared of x can be written as 1/2 times 1 plus cosine of 2x. So by the way, why would we use this formula and not the Pythagorean formula? Well, the Pythagorean formula would just replace cosine squared with sine squared, which is just as bad. The advantage of this formula is that it gets rid of the exponent, right? It brings us down to something that does not have an exponent so that we can actually find the antiderivative. So now we have the integral of 1/2 times 1 plus cosine of 2x dx. So let's clean this up a little bit. Let's pull the 1/2 outside of the integral. And so now we just have 1 plus cosine of 2x dx. And so from here, we can now split this into two integrals. I mean, you don't really have to, but I think it might just make things a little easier. So if we split this into two integrals, one is the integral of just 1, and then the other one is 1/2 times the integral of cosine of 2x dx. So for this second integral, this is one where you could do a substitution. So you could let u equal to 2x, and then du would be equal to 2 dx. This is the type of substitution, it's totally fine if you do this and you write out the substitution. This is one that I think you might find it useful to be able to kind of do in your head. So what do I mean when I say that? Well, you might guess that the antiderivative of cosine of 2x would be sine of 2x, right? But the problem is that 2, the chain rule, throws in something extra. And so really, the antiderivative of cosine of 2x is going to be sine of 2x divided by 2. And again, it's totally fine if you write out the u substitution. I just want to mention it because I think, it can really bog you down if you always have to write out everything every time. And I think it's nice to kind of have that intuition and be able to do it in your head. So what do we get for this first one? Well, the antiderivative of 1 is just x. And so then here, as we said, we get 1/2 times sine of 2x over 2. And then we have plus c. So from here, we can just kind of simplify things a little bit. So we have 1/2 x plus sine of 2x over 4. And maybe let's just make a common denominator because why not? So this would be 2x plus sine of 2x over 4 plus c. All right, so let's do another one that is going to make use of this same type of formula, but a little bit more complicated. So now let's do the integral of sine squared of, sine to the fourth of x is what I meant to say. Okay, so basically anytime you have an even power of sine and cosine, you want to be thinking about using these identities that we just introduced. And so in order to make use of these identities, what we can do is we can rewrite this as sine squared of x squared. And so now we can use the identity we saw on the previous page. So on the previous page, we saw that sine squared of x can be written as 1/2 times 1 minus cosine of 2x. And so we can go and put that in. And so we end up with the integral of 1/2 times 1 minus cosine of 2x. This whole thing squared. So we're going to actually FOIL this out and multiply it out, but let's actually get rid of this 1/2 first. So 1/2 squared is 1/4. So we can just bring that 1/4 to the outside of the integral. And now we're just left with 1 minus cosine of 2x squared. So what happens if we multiply 1 minus cosine of 2x with itself? Well, we're going to get 1 minus 2 times cosine of 2x plus cosine squared of 2x. All right, so from here, it might look like we just have something that's more complicated, but we actually will be able to do this part using the same approach that we used on the previous problem. So, or even on this problem, right? We're going to use that same identity that will allow us to take this cosine squared and get rid of the square. And then for the rest of it, we can split it up, right? So we can rewrite this as 1/4 times the integral of 1 dx minus 1/4 times the integral of 2 times cosine of 2x dx. And then now we have plus the integral, plus 1/4 times the integral of cosine squared of 2x dx. Okay, so let's maybe get these first two out of the way, and then we'll focus on the last one, because the last one is kind of the trickiest part here. So the first part, so the antiderivative of 1 is just x. We have 1/4 x. And then this next part, you could pull out the 2, but actually as it is 2 times cosine of 2x, the antiderivative of that is just sine of 2x, right? Because the derivative of sine of 2x would be cosine of 2x times 2. And so the antiderivative of 2 times cosine of 2x is just going to be sine of 2x. You would get the same answer if you pulled the 2 out. Okay, so now let's focus on this part. So for cosine squared of 2x, we want to again make use of that identity. So we know that if you have cosine squared of x, we know we have that formula actually written right here, right? So cosine, let me find it. Cosine squared of x is 1/2 times 1 plus cosine of 2x. So now all we have to do is, instead of having an x in this first part, we're going to put a 2x there. So what's going to happen on the right-hand side if we have a 2x there? Well, this will just be 4x, right? Because basically, what is this formula saying? It's saying whatever's in these parentheses here, you want 2 times that in these parentheses. And so if the original parentheses have 2x, then that means that the second set of parentheses will have 4x. So we can use that identity. We can say cosine squared of, 2x is going to be equal to 1/2 times 1 plus cosine of 4x, which again, it looks more complicated, but it will be easier for us to integrate. And so now we're going to have plus, so maybe let's kind of set this part aside and we'll add it back in when we're done, just because otherwise this is going to get to be a very long string of algebra. So let's focus on this part and then we'll put them back together at the end. So here we're going to get 1/4 times the integral of 1/2 times 1 plus cosine of 4x dx. So we can rewrite this as 1/8, so pull that 1/2 out, and now we have the integral of 1 plus cosine of 4x. And now we can split this up again. So now we have 1/8 times the integral of 1 dx plus 1/8 times the integral of cosine of 4x dx. So what's the antiderivative of 1? That's just x. So we have 1/8 x. And then here, using that same kind of reasoning from before, the antiderivative of cosine of 4x is going to be sine of 4x over 4, right? Because the derivative of sine of 4x would be 4 times cosine of 4x. And so we need that 1/4 to counteract that. And so we're going to have 1/8 times sine of 4x over 4, and then we should throw in the plus c because we didn't do that earlier. Okay, so now let's link this back up with what we had above. So, sorry, my screen is stuck. Okay, so we had 1/4 x, so now we have 1/4 x plus 1/8 x, and then we had up here sine of 2x over 4. And now we have plus sine of 4x over 32. And then this entire thing is plus c. And so this is our answer. So, not the fastest derivative to calculate, right? There was a lot of little steps there. But the point, again, of this formula is that at least it makes it into something that you are capable of integrating, right? Even if it's a little annoying, at least you are capable of doing it, whereas when it was squared, you don't have an antiderivative for that. All right, I want to do just one more example in this video, basically to bring up one other formula or one other trig identity. So let's say that we wanted to find the integral of x times sine of x squared times cosine of x squared. So first of all, notice that the sine and the cosine both have an input that's not just x. And so we can't really jump into any of the identities or anything like that just yet. So what we can do instead is we can do a substitution. So what makes me think of doing a substitution with the x squared? Well, the derivative of x squared is is 2x, and we have an x right here. And so that substitution is going to work out. So let's let u equal x squared. And that means that du is going to equal 2x dx. And so notice that we don't have 2x dx, we have x dx. And so what that means is that if you wanted to do this without actually solving for dx, you basically just need to incorporate an extra factor of 1/2, right? Because we don't actually have what we need for du, we have half of it. And so we can rewrite this as 1/2 times the integral of sine of u times cosine of u du. So that du came from the x and the dx, but also the fact that we have a 1/2 out front. Together, those things let us put the du in. Okay, so now what should we do? Well, there's actually a couple of approaches that work here. You could use another substitution. So if you let let's say w be either equal to sine or cosine, that would work. That would actually get you to the answer. But I want to just, because we were talking about it before, show you another method. So another method would be to use the identity that says that sine of u times cosine of u is equal to 1/2 of sine of 2u, right? That was this identity at the bottom. So we have sine of u times cosine of u. And so that's going to be equal to 1/2 times sine of 2u. So let's pull that extra 1/2 outside. And so now we have 1/4 times the integral of sine of 2u du. So now again, we could do a u substitution, or I guess a w substitution in this case, but again, I think this is a good example of one that you should be able to kind of figure out without having to write it explicitly as a substitution, because the antiderivative of sine of 2u is going to be cosine or negative cosine of 2u divided by 2. So we can say 1/4 of negative cosine of 2u divided by 2. And so our final answer, actually not quite final, but our almost final answer would be negative cosine of 2u over 8 plus c. And then the last step is to put back in what u was. So remember, u is equal to x squared at the very beginning of the problem. So we now have negative cosine of 2 times x squared over 8 plus c. And that's it. So that's it for this video. And in the next 2 videos, we're going to be getting into something that sounds like it's similar, but it's actually pretty different, called trigonometric substitution. So we'll be starting with integrals that do not have trig functions in them, and then making a substitution to turn them into integrals that do have trig functions in them. And so that will allow us to make use of some of the stuff that we've talked about in the last couple of videos. I will see you next time.